Welcome to 8th lecture of Analog Integrated Circuits Design. So far we are discussing about common source amplifiers, CS amplifiers. In the past 2 to 3 classes we looked at common source with resistive load. Then we have come across something called as a diode connected load, and we saw different variants of diode connected. The first one was whatever you have seen is of this type, where you have a diode connected NMOS load. Then we saw that when you write the gain expression, body effect also will come into picture, and that will slightly reduce the gain. In order to remove that, or in order to remove the effect, or in order to have a better gain, we went for the second circuit, which is instead of NMOS diode connected, you have PMOS diode connected. But then we saw that there is a problem in the output voltage swing. I hope you remember this, because when we analyzed the circuit, there were two things we observed. One is when I look for a specific gain, I could see that there is a disproportion in the size of the transistors, and also we saw that when we looked at the overdrive voltages, or the ratio of overdrive voltages, overdrive voltages requirement for either of the transistor will be high, and as a result of that your output voltage swing will be very much affected. So generally the space for the output voltage to swing, in this case you can see that I have drawn a pink color line here. So the space for the output voltage to swing is otherwise called as headroom. So today onwards we will use that this word here, headroom. We call this as headroom. So what is headroom? Headroom is a space for the output voltage to swing. So now we saw that since the overdrive voltages are more, the headroom is less, or overdrive voltages are basically consuming the space for the output voltage to swing. I'll repeat about headroom in today's class. So from then, now we are at this case where we tried all the four variants, where two NMOS input and two PMOS input with the same PMOS load and NMOS load. And if you remember in the last class, we also said that the output nodes of all these configurations are low impedance, and for that reason the bandwidth available will be more. Bandwidth understood as a advantage of the circuit. So today we will continue this diode connected, but we will do a small modification in the existing circuit in order to rectify, in order to come across the disadvantage what we saw in the previous circuit, where there is a terrible hit in the output voltage swing, right? So we will continue this. So what we will see today is CS amplifier with a diode connected, PMOS load. But there we will see a slight modification in the circuit. So we will, for that reason, we will call this as PMOS load itself, but we will just say this is a modified one. That means the previous circuit exists as it is, but we will do some changes here in order to come across a difficulty what we saw in the previous circuit. So the previous circuit was this, NMOS input and PMOS diode connected. So I am just using the same circuit here, PMOS diode connected and NMOS input. Are you guys with me? Can I get some response in the chat box? All right. Thank you for the response. So this is M1, this is M2, and this is VDD. All right. Now, what I said is, we know. See, I hope, and you guys remember about the discussion what we made on this circuit. Now, since there is a problem in the ratio of overdrive voltages, or basically, I'll just write down about headroom here. What is headroom? Headroom is a space available for the output voltage to swing. this is headroom. Now we saw that in this circuit, the your see, because of overdrive voltages, your headroom area is actually consumed by the overdrive voltage. That is what we call it as headroom consumption, right? So headroom is basically the space for the output voltage to swing. Now since the overdrive voltages are more, that space is getting reduced, or that space is getting consumed. Now, in order to come across this issue, what method is suggested is we are adding one current source in parallel to this M2 transistor. One current source is added in parallel, and I'm calling this current source as IS. So previously, till before adding this current source, we know that the current through M1 and M2 are equal, right? But now that is not true. This is ID1, and this should be considered as ID2, and there is some other current source called IS, right? Now IS can be of any factor. So let's say, for example, if I am providing an IS which is equal to say 3/4 of ID1, that means the ID1 current 3/4 is coming from IS, and the remaining 1/4 is coming from M2, whatever it is. For in whatever way we can think, the idea here is we are adding an additional current source in parallel to M2, right? And say, for example, I am considering IS is 3/4 of ID1. So what is ID2? ID2 will be 1/4 of ID1. So IS plus ID2 is equal to ID1. That is how I have written here. So IS plus ID2 will be equal to ID1. That is the current equation here, right? So if you write an equation at this node, sum of the currents entering the node is ID1 plus IS, ID2 plus IS, and the sum of the current leaving the node is equal to ID1, right? So that is what I have written here. Now, if I am trying to calculate the gain for this circuit, let me ask this question to you guys. So what will be the gain for this particular circuit? Can I get answers from your side? What will be the gain for this circuit? Adarsh, are you there? Adarsh Gupta, yes.
Yes, sir.
Yeah. What is the gain of this circuit?
Sir, so one second.
Yeah.
Sir, it's GM1 minus GM1
Hmm.
into 1 by GM2
Hmm.
parallel R01 parallel R02.
Yes, that is true. If I am neglecting R01 and R02, I can directly write it as minus GM1 into 1 by GM2, or I can say it is minus GM1 by GM2.
Yes, sir.
Yeah. Thank you, Adarsh, for that. So now for others who are wondering what about this IS? IS is an ideal current source what I have added. So there is no resistance across. No, it is not like no resistance. The resistance across the ideal current source is equal to infinity. So finally, your gain expression will be ID1 is equal to minus GM1 divided by GM2 will be your gain expression. Now, if I substitute the expressions for GM1 and GM2 in this, I can write it as under root of anyway, numerator and denominator both is having square root. So I'm just placing a common square root here. And for GM1, I will write it as 2ID1 mu n Cox W by L of 1 divided by denominator GM2 is equal to 2ID2 mu P Cox W by L of 2. All right. I hope this is clear. Now, so let mu1 and mu p, let it be there. We know mu1 and mu p are not same. There will be some mu1 is approximately equal to twice mu p is what commonly we take it as a ratio, because the mobility of holes are lesser compared to mobility of electrons. But now previous case, we were cancelling out ID1 and ID2, but in this case we cannot directly cancel it because ID1 and ID2 are not equal. Or I can say that ID1 is equal to 4 times ID2 straight from this expression. So now this again depends on how much IS we are providing. So in this case, I have taken a typical example of IS as 3/4 of ID1, and that will give you an ID1 equal to 4 times ID2. Now, if that is the case, can you guys tell me what is the gain even by substituting ID1 and ID2 into this? Can you tell me what is the gain here? Kavana, are you there? Kavana?
Yes, sir.
Yeah, Kavana, can you tell me what will be the gain expression now after substituting ID1 equal to 4 ID2 in this case?
Sir, it may be like minus GM1 by 4 GM2.
No, that expression I have written already. Now you can see on the screen there is under root of 2 ID1 mu n Cox W by L of 1, and that formula you can see, right?
Yes, sir.
Yeah, now there if I am substituting ID1 equal to 4 ID2 and cancelling out the other terms, what will be the final expression from that? Whether my question is clear?
Yes, sir. I'm thinking.
Okay, all right. Yeah, let me check with some other. Yeah, Nisha, are you there, Nisha? Nisha, are you there? Can you respond even by a message in the chat box if you are there? All right. Yeah, you okay? Yeah, okay, Nisha. Yeah. Let me check with Harsh Pratap. Harsh, are you there, Harsh? Dhananjay Kumar.
Yes, sir. Yes, sir.
Yeah, tell me, Dhananjay.
Sir, 2 mu n W by L1 divided by mu
Hmm.
p W by L
Uh,
2.
W L of 2.
Yes, sir.
So that means square root is there or not?
Yes, sir. Square root is there.
So minus 2 and then square root mu n W by L of 1 divided by mu p W by L of 2. Yeah, I hope this is clear. This is a gain expression, and now when you substitute mu n as twice mu p, you can definitely get some gain out of this, and you can choose a specific WL ratio as well. That is possible. That is all right, Harsh. I understood. Probably you would have, yeah, I know that. Yeah, probably you would have just swiped across your mobile and you would have exited from the meeting. That is okay. No, yeah. So I think I got answer from Dhananjay. Yeah, thank you, Dhananjay, for that. Now let me check the improvement. So why we have done all these things by adding this additional current source is just to verify or just to improve the output swing. So that is my next objective here. So I'm going to verify uh, whether there is any improvement in the swing. So how will I verify the improvement in swing? That I'll verify by looking at the ratio of overdrive voltages, whether the overdrive voltages values are high or low. So in the previous example, on the previous case, when you verified, you saw that the ratio of overdrive voltage is coming exactly as 10 when you tried for a gain of 10. Now let us see what will happen in this case. So as we saw, as we have discussed here, ID2 value is equal to 1 by 4 ID1. So in order to get the ratio of overdrive voltages, previously we equated current. In this case, we have to equate current, but the current values ID1 is not equal to ID2, rather ID1 is equal to 4 times ID2. Right. So I'll write it as ID1 is equal to 4 times ID2, and then we'll write for mu n C of W by L of 1 VGS1 minus VT the whole square is equal to half mu P. Yes. So that is equal to 4 times half mu P Cox W by L of 2 into VGS2 minus VT the whole square. Right. So if you solve further, let me take this to the next page, or let me write it over here itself. VGS1 minus VT divided by VGS2 minus VT can be written as, so half and half you can get cancelled, then Cox values you can get cancelled, so the remaining will come as under root of 1 by 2 into mu n w by L of 1 divided by mu p w by L of 2. So you will be wondering what all equations I'm writing. So the whole idea is just to understand, by adding this current source there is an improvement in the circuit behavior. So just to summarize, what I will do here is I'll write down both swing and gain expressions together, right? So in next page I will write gain expression was minus 2 into under root of mu n w by L of 1 divided by mu p w by L of 2. This was gain expression. Similarly, the ratio of overdrive voltages was VGS2. Uh, then I have written VGS2. No, I have written VGS1 minus VT, right? Let me just check.
So I think it should be inverted. LHS
It
one.
should be inverted. Yes, that is right. So this should be VGS2, right? And this is 1, isn't it?
Yes, sir.
Yeah. So VGS2 minus VT. So let me write it as VTP because it is PMOS and denominator is NMOS VTN, which is equal to half into under root of mu n W by L of 1 divided by mu P W by L of 2. Right. Now this is the ratio. These are the expressions for gain and ratio of overdrive voltage. Now can you tell me how will I so previously we saw that so previously we saw that ratio of overdrive voltages were exactly equal to gain. Now what is the case? Now what is the ratio of overdrive voltage, whether it is equal to gain or it is a fraction of gain? Can I get some answers from you guys? Let me check with Chetan. Chetan SM. Yeah, yes, Bhuvan. Yeah, I'm just waiting for Chetan. Are you there? Yeah, Chetan, can you tell me what is the ratio of overdrive voltages in this case? Yeah, anyway, Bhuvan responded for that. That is equal to AV by 4. That is true. So VGS2 minus VTP by VGS1 minus VTN is equal to AV by 4. And I think the rest is self-explanatory because previously the ratio of overdrive voltages are exactly equal to gain. But in this case, it is gain divided by 4. So if I am considering the same example of gain as 10, now ratio of overdrive voltages will be what? It will be VGS2 minus VTP divided by VGS1 minus VTN, which is equal to 10 by 4, which is equal to 2.5, right? So now if I am considering VGS1 minus VTN as say the same value 200 milli, now your VGS2 minus VTP will be 2.5 into 200 milli, which is equal to 500 millivolts, right? Now if I go back and see in the voltage headroom, or how much will be my output voltage to swing across now, this is 0 and this is, say, I think we have taken a supply voltage of 3 in the previous case. Yes. Now what is the bottom transistor's overdrive voltage? It is as low as 200 milli. it is only 200 milli it is required there, and for the top transistor it is slightly taking more than that, which is around 500 milli. This is the overdrive voltage requirement. This is VGS2 minus VTP, and this is VGS1 minus VTN. Now you can see that if you properly fix an output DC voltage here, you can see that you have a lot of room for the output voltage to swing. Or basically this is your headroom, this is headroom, and I can say headroom consumption by the overdrive voltage is less, or I would say output voltage swing at output improved. Do you have any questions on this? So what we did is we added an additional current source, and we observed that because of that additional current source, the ratio of overdrive voltages are not exactly coming as equal to gain. It is a fraction of gain, and therefore we can have a better output voltage swing in this case. I hope this is clear, and if you have any questions, please post it here, or even you can ask me at the end of the session. Now moving on, I'll quickly go through two more variants of transistor amplifiers. Now there is a one question remaining here. I told that we are actually keeping a current source, and I also mentioned that this is ideal, but we know that this placing an ideal current source in parallel is only an ideal thing that cannot be realized in practice. In practice, you have to bring a real current source here. When I say real current source, I have to use transistor itself as a current source. So we'll talk about current source load little later. Before that, let me bring to you one more another structure, one more another variant of this. So one thing to remember here is, you can definitely say theoretically that the CS amplifier with the diode connected PMOS load with a modification can have a larger voltage swing, but that all depends on how far we implement this current source here. So I have an ideal current source, so how ideal we can bring in, or how ideal we can design a current source in the circuit will be the key point where you will have a proper improvement in the gain or not. All right. So moving on, I am just bringing you to another variant that we call it as CS amplifier with a triode load. So what we are doing here is, we started with CS amplifier with the resistive load, and probably you remember we started with CS amplifier with resistive load, and we saw that the maximum resistance can be, yeah, so the maximum resistance to this can be by placing R0 as infinity. So that will give you the intrinsic gain from the MOSFET. So but that is not possible, but to keeping an ideal current source is not basically possible. That is why we talked about various other variants. Starting from resistive, we had diode connected, NMOS and PMOS, and then we have modified diode connected. Now we are coming to another one that is called as triode load. Even though this is not widely used one, you should know that there is one kind of this variant. So what we do basically is, we will go for only PMOS load when you have an NMOS input. Maybe now you can say the reason why you will use PMOS as a load, because body effect also will not be there. Now this is M1, and this is say M2, and this is output V out, and this is VDD. Now this is suitably biased, but we'll make sure that this biasing, so this V bias will make sure that this will drive transistor M2 in linear region. Transistor M2 in linear region. So when I say linear region is otherwise called as triode region. That is why we have the name of the load as triode load, right? So we'll drive M2 in linear region or in triode region. Both are same. If that is the case, can you let me know what will be the condition of this transistor M2? I told that that is in linear region. So how will I write the gain expression here, AV? How will I write AV? Assume that lambda is equal to 0 for M1. What will be gain AV for this circuit? Any answers? Or how will this M2 transistor behave as it is in linear region? How will that transistor behave? Anirudh? Yes, Sri Harsha, that is right. Small value resistor, very good. Yes, Sri Harsha. Bhuvan, Avinash, yes. All are responding it, that will be a resistance. Now, if that is a resistance, I can definitely write. So then you should understand one thing. If your M2 is in linear region, then the small signal model is not applicable there. You can think of that transistor as a resistor. So if that is the case, I will write the gain expression as, what is gain? So gain is nothing but the I can write gain as GM into R. Or what is GM? GM is the GM of the input runs. That is why I wrote it as GM1. What is output resistance? Looking down, since lambda is 0, this is infinity. Looking up, it is the resistance of the MOSFET. So I can write minus GM1 into R on, where this R on is considered as the on resistance of the MOSFET when it is in linear region, and that can be written as 1 by mu p Cox W by L into VGS minus VT. Now, if you're wondering from where I wrote this equation, this is straight from the current equation of a transistor in linear region, MOSFET in linear region. ID is equal to half mu n Cox W by L VGS minus VT into VDS minus VDS square by 2. This is the expression for a linear region. Now, when you assume that your VDS is small, VDS square can be neglected. Now, again, if you are wondering why I said that VDS is small, since it is in linear region, VDS should be definitely small, right? Your VDS cannot be greater than VGS minus VT. That is for saturation region condition. For linear region condition, your VDS should be smaller than VGS minus VT. And in that case, if that is small, VDS square can be neglected, and that will lead to the expression where you have ID equals half mu and Cox W by L VGS minus VT into VDS. Now, if I look for a resistance, so the MOSFET is acting as a resistor between the terminal source and drain. So to get the value of resistance, I'll write what is VDS by ID, which is equal to what is sorry, this half is not there in the expression, right? Yeah, this is the expression. There is no half. So what is VDS by ID? 1 by mu n Cox W by L into VGS minus VT. This is called as on resistance of the MOSFET. Now in our case, since it is a P MOSFET, I have written on resistance as mu P Cox W by L into VGS minus VT, right? This is on resistance. Now, okay, so this circuit I have taken to understand that there is a variant called as triode load, but in general this is not used as an amplifier for the very simple straight reason that this transistor is not in saturation region, right? So we know that in general we use, or we need transistors to be in linear region. Now this, sorry, saturation region. Now this transistor is in linear region. That is one reason why we will not use this as an amplifier. I'll tell you what are the other reasons. You can see that from this expression, mu p, so the on resistance is having mu p. So mu p is definitely, mu p is something which is not a constant. It can slightly vary. It depends on temperature, because mu p varies with the temperature. You will also see a variation to VT. Threshold also can vary. Threshold VT also can vary in a MOSFET. Now, if mu p and VT varies, I can say R1 will vary. That R1 is a variable. R1 is basically a variable when there is a change in temperature, when there is a change in we call some, yeah, so Vt can vary, and that we consider as a voltage variation, right? Now altogether this mu p Cox, this constant also I can consider that there can be some variation. We call it as process variations, right? So what all variations are there? There can be process variations, there can be voltage variations, there can be temperature variations. All these variations together we call it as PVT variations. This you will see or you will hear about PVT variations many times when you study IC design courses. There can be variations in process, there can be variations in voltage, there can be variations in temperature. So as a result of all these things, we can always say that R1 will be a variant. If R1 is a variant, what will be your gain? Gain also will be not constant. Yes, Amitesh, I'll answer your question. Now, if R1 is a variant, your gain also will vary. So gain can vary. Now, in general, unless if our need is a variable voltage gain amplifier or a variable gain amplifier, in common or in general, we need all amplifiers should have a constant gain, right? So if that is the case, I cannot use this amplifier for the simple reason that the gain itself is varying. So as your gain is varying, this amplifier is rarely used. Now coming to Amitesh's question, so Amitesh is asking how are these variations caused? So as I mentioned, as temperature changes, mu p can change, right? Now, if mu p is changing, mu p Cox term or the combined value of mu p Cox will vary. So that mu p Cox variation itself is considered as a process variation because mu p Cox is identified as a process parameter. Now, if mu p varies, mu p varies due to temperature, mu p Cox also will vary. So that is identified as a process variation. Now, threshold voltage also will have certain variations. So threshold voltage variations also will come as a part of voltage variation, right? So these variations in general, due to physical parameters, these variations can cause. The main reason is temperature. Another can be what we call it as process variation, which is a combined term called mu and Cox. Is that clear, Amitesh? Yeah. Thank you, Amitesh, for that. So gain can vary or gain is not constant. So I would say this amplifier is not used as such. This is not a widely used configuration, or instead of telling it as widely used, this is something which we um, very rarely use, or this will be used, will not be used. That also I can say. So now, if you ask me the question, why then you brought this amplifier as an example here, is for the simple reason to understand that a MOSFET in linear region as a load in an amplifier will not have any useful application, right? All right, so that is all about CS amplifier with triode load. And now coming to the most interesting and useful circuit, that is CS amplifier. Again, it is CS amplifier variant with current source load. CS amplifier with a current source load. All right, so can you guess what will be the circuit diagram for this? Previously, it was a triode load and the MOSFET was in linear region. Now, if MOSFET is in saturation region, I can directly say that that is a current source load. So, you will have a P MOSFET there. This is V in, this is V out. This transistor is M1, this is M2. This is suitably biased so that M2 will be in saturation. So V bias will drive M2 to saturation. M1 also should be in saturation, and that should be yes, Sri Harsha, in place of Hello, am I audible? All right. Yeah, sorry, I got disconnected in between. So we were talking about. Okay, let me. Yeah. So we were talking about this circuit, and as I mentioned, this V bias will drive M2 to saturation. Now, can you tell me what will be the voltage gain for this circuit? AV voltage gain. Any answers for that? Minus GM into R naught, intrinsic gain of M1. All right, intrinsic gain of M1 is GMR naught, but what about M2 device? M2 is in saturation. Okay, now I'll mark that lambda is equal to not equal to 0 for both cases. Then what will you say? Very good. Yes, Bhavya. So we know that voltage gain is equal to voltage gain is minus GM into R out. In this case, GM is minus GM1 of M1 device. Now resistance, if I look at the circuit diagram, down I can see R01 and top I can see R02. In that case, your gain is R01 parallel to R02 into minus GM1. All right. So this is your gain. Right. Now, if you look at this gain, or if you look at this gain expression compared to the other gains what we have written, what can you comment directly? What I'm asking is whether the gain magnitude is small or large compared to the previous cases. Whether it is large or small. Any answers? Whether it is large, gain is large. Yes, it is larger. Why it is larger? In all the previous cases, you had a term called as minus GM1 into 1 by GM term was there. So your gain was actually smaller then. Now, this by looking at this expression, you can make some comments here. The very first comment is your gain is large. You have a large gain. That is the very first thing. Gain is large. Now, second factor is, can you tell me what kind of output impedance, looking at the output node? Can you comment something whether the output node is a low impedance node or a high impedance node? Okay, so I wrote that gain is larger because the resistance here is large. This is large because two drains are tied together. So I will write here drain terminals of transistors are tied together. If drain terminals are tied together, the output impedances, instead of writing output impedance, output node is a high impedance node. All right, is that clear? So output node is a high impedance node because drain are tied together. So if you look at the previous cases, we told that output impedance is output node is low impedance. Did I say that before? Yeah, output node is low impedance because you can see that one source and one drain. So always the resistance seen at the source is smaller. So if a source and drain are tied together at the output node, then your output node itself will be a low impedance node. But in this case, two drains are tied together. That is why your output impedance is actually a high impedance node. Right. So large gain is one thing. High impedance output node is another observation of the circuit. And the lastly, if you look at the output voltage swing, I will directly write the output voltage swing as from VDD. Now there are two transistors, both should be in saturation and both should have its own overdrive voltage. So if I draw the voltage headroom here, I would say this is 0, this is VDD. Now the top transistor should have some overdrive voltage and the bottom transistor will have some other overdrive voltage. The rest of the voltage is, or rest of the room is for the output voltage to swing. So with that, I will write the expression for output voltage swing as VDD minus VOD1 minus VOD2. So overdrive can be written as VOD or VOV. Both are used. Right. We will talk little more about current source load on a later class in the coming classes. But for today, these are the things we should understand about this specific circuit. Any questions on this? Yeah. Now, yeah, I have a question. How will body effect be applied if we use NMOS load in this and previous configuration? All right. So maybe for this, if you want to use common source amplifier and to make sure, okay, maybe I think you can only answer this question. Avinash, yeah, and even for others also, the circuit what you are seeing on screen now, can M2 be replaced with a NMOS? That is my first question. In place of M2 PMOS, can I replace M2 with an N MOSFET? What will be your answer for that? Can we use? So the answer should be either yes or no. If it is yes or no, then I also want to know the reason for that. Okay, so I would say I cannot use M2 as an NMOS device for the simple reason gain is low. Okay, for the simple reason, if I use NMOS as M2, it cannot act as a current source, and that we have actually dealt before by taking four examples, which all configurations can be used as a current source. Maybe, yeah, now maybe you can relate that. So I'll take you to that specific question. Where did we see that? Yeah, you see here, yeah, out of these four configurations we eliminated the last two, and the first two are we call the first two only can the first two transistors only can operate as current source. So in the first one, you can see in figure A you have a transistor, that is what our input transistor is in the current circuit what we used. In figure B also you have a transistor, and that is actually our load transistor. You see here I mentioned that a circuit will be attached here. What is that circuit now? In our present circuit of CS amplifier with a current source load, the circuit what I meant here is nothing but the input NMOS transistor. Right. So for coming back to Avinash question, so Avinash, your question is, if I replace PMOS with an NMOS load in this fashion, that is figure number D, what will be the effect? You asked about the effect of body, but I would say even I cannot use NMOS as a current source load in this case, right? I hope you can you are able to relate this. In figure D, again the circuit is nothing but an input transistor. But if you place an N MOSFET in place of a P MOSFET, that cannot act as a current source, right? If that cannot act as a current source, then that is not our present circuit, no? And you can also, so why it cannot act as current source? For the reasons what I mentioned here, it cannot keep a constant current, it cannot give a high output impedance. right? So since that is not possible, then no need to actually discuss about the effect of body, because body effect will be definitely there, but it cannot act as a current source load. Is that clear, Avinash? Yeah, and as Bhavya told, gain is low, but the very first answer should be it cannot act as a current source. Yes. If you have further questions, you can ask. Please stay back. Thank you so much for joining.